Hello and welcome to this video on the inverse Laplace transform. So if you've been following our previous video, we introduced the topic of the Laplace transform and we looked at some simple examples of converting functions from the time domain into the S domain. In this video, we're going to do the opposite process. We're going to take functions in the S domain and convert them back into the time domain using the inverse Laplace transform. And again, like in our last video, we're going to do this by referring to a table of standard Laplace transforms, like this one here. And we'll jump straight in with an example. Let's suppose that we want to find the inverse Laplace transform of this function here, 1 over s squared plus 4. And you'll notice that the inverse Laplace transform is denoted with this scripted L to the power of -1, the inverse Laplace transform. And again, we enclose the function that we want to transform in curly braces, like so. So if we take a look at this function here, the inverse Laplace transform is a little bit trickier than the Laplace transforms that we looked at in our previous video. And there's a little bit of cleverness involved to try and rearrange the function into a form that resembles one that's in the table. So if we have a look in the table, the closest entry for the function that we are asked to transform is probably this one here, the entry for a sine function. And it's best maybe to look at these side by side. So here's our problem that we've been asked to apply the inverse transform. And here's the table entry for our sine function, omega over s squared plus omega squared. Now, assuming this is correct, and it seems to be the closest, we run into a problem here because on the bottom here we have this number 4, which seems to correspond with omega squared. So that means that omega must be 2, because 2 squared is 4. But then on the top of the function here, we also have omega. But with the problem we're given, there's 1 on top of the fraction, whereas we've said that omega is 2. Now, as it happens, this isn't really a problem. We're going to cheat a little bit, and what we're going to do is simply double our expression. So rather than 1 over s squared plus 4, we're now going to have 2 over s squared plus 4. And to make that balance, because we've doubled this expression essentially, which we're not really allowed to do, we're going to multiply the whole thing by a half to cancel that out, as it were. And so now we have, rather than 1 over s squared plus 2 squared, we now have a half times 2 over s squared plus 2 squared. And this arrangement, this fraction here, now satisfies the table entry that we saw for the sine function. And when we apply the inverse Laplace transform, if you remember from our previous video, we're allowed to pull coefficients outside of the Laplace transform, and it's the same here with the inverse Laplace transform. We can take this half outside of the inverse Laplace transform, and so now we have a half times the inverse Laplace transform of 2 over s squared plus 2 squared. And looking at the corresponding entry in our table, we see that that's going to give us a half, because the half hasn't been affected by the transform, times sine omega t. Well, omega is 2 in our case, so sine 2t is our result. Here's another example. Let's suppose we're asked to find the inverse Laplace transform of 3 over 4s minus 1. So again, referring to our table, there's nothing in the table that exactly matches our requirements. The closest is probably the entry for exponential growth here. So let's see these side by side. We're quite close, but we can perform a few steps to get our problem to look similar to the form that's in the table. So rather than 3 over 4s minus 1, let's pull out a common factor of 4 on the denominator of that fraction here. And so now we have 3 over 4 multiplied by s minus a quarter. We've taken 4 outside of the brackets for both of those terms. And so here we've got this a numerator of 3 on the top of our fraction and denominator a coefficient of 4. And so what we can do is we can break that down into separate terms. Rather, we can say that that's equal to 3 over 4 multiplied by 1 over s minus a quarter. So by pulling out that factor of 3 over 4, 3/4, we've now got our function in the form that's required. And we can perform the inverse transform. Again, like in our previous examples, rather than applying the inverse Laplace transform to that whole expression, we can pull that coefficient of 3 over 4 outside of the inverse Laplace transform. And so we're left with something that looks like this. We have 3 over 4 multiplied by the inverse Laplace transform of 1 over s minus a quarter. And looking at our corresponding function of t in the table, we'll see that this this term minus a quarter or is minus a in our table, and that's going to correspond with 3 over 4 e to the power of a quarter t. One thing to watch out for is, even though that a term is negative in the s domain, we have s minus a on the bottom of the fraction there, it's a positive term in our t domain, the time domain, when we refer back to the table there. Let's look at one more example. We have the inverse Laplace transform of 2 over s squared plus 6s plus 13. And when we examine this particular problem, none of the transformations available in the table are immediately obvious as being suitable to match ours. The closest is probably the decaying sine function. And again, we're going to have to do some rearranging, this time by factorization. So let's see these side by side again. And we see that our denominator of s squared plus 6s plus 13 doesn't factorize neatly into the form of s plus a squared, where a is a given number here. We can't factorize that quadratic expression there into this form. But let's suppose it wasn't s squared plus 6s plus 13. Let's suppose it was s squared plus 6s plus 9. Now that does factorize into the form of s plus 3 squared. But remember, what we've done really is we've cheated. We've taken 4 away from our expression. We had plus 13 and we've changed this to plus 9. We've subtracted 4 essentially. And so we have 4 left over to add on the end. And so really now our problem is now in the form of this. We have 2 over s plus 3 squared plus 4. And looking back at our form of the decaying sine function in the s domain, we now have omega seems to be equal to 2, because we have omega squared on the bottom, and that corresponds with 4, and omega on the top corresponding with 2. And our a term, enclosed in this squared bracket here, is going to be 3. So back in the time domain, we were told that this converts to e to the minus at sine omega t. Well, knowing the values of a and omega, we can say that that's equal to e to the minus 3t sine 2t. Just as a point of interest before we finish this video, that result that we've just found there for the decaying sine function, we're hopefully familiar with sine functions in the form of a sine t, for instance, where a would be the amplitude. But now we have a function that looks like this, e to the minus 3t sine 2t. So the frequency's doubled here inside the argument for the sine function. But notice this amplitude here is not a constant. It's this decaying exponential function that's going to decrease over time. And so putting these two together, rather than a sine wave with a continuous amplitude, we're going to get a sine wave whose amplitude decreases as time goes by. And this particular function, for instance, if we plot between time equals 0 and time equals 3 seconds, we see that this sine wave very quickly reduces to an amplitude of 0 in just a few seconds there. So I hope you found this video useful in introducing the inverse Laplace transform, along with the Laplace transform that we looked at in our previous video. In our next video, we're going to look at how we can put both of these processes together to solve complicated differential equations.